One of the things that integration allows us to do is calculate the area under the curve. The basis for that is the idea of what's called a Riemann sum. If I draw a curve and I wish to find the area under that curve, you can think of that as the area of all the squares underneath. So if I were to draw two rectangles approximating the area of this curve, I could take the area of each rectangle, which would be this distance times this distance, and then I would add the two together. If I wanted to find the area under the whole curve, I could continue to draw multiple rectangles and approximate the area under the curve. The fundamental theorem of calculus tells us that the area under any nice curve from some x value a to some x value b is calculated using the antiderivative or the integral. As an example, let's consider this function. We want to find the area under the curve. To do that, we must first find the antiderivative, and the antiderivative is found by calculating the integral of the function. When I use my integral rules here, I find that the area or the antiderivative is going to be 30x minus 20x squared over 2 plus x to the 6 over 6 plus c. This simplifies to 30x minus 10x squared plus x to the 6 over 6 plus c. Now, the fundamental theorem of calculus tells me that I can then approximate the area under that curve using the values a and b, in this case, 1 and 2. And I will do f of 2 minus f of 1. So I'm simply going to plug these values in. When I plug in f of 2 to this equation, I get 30 times 2 minus 10 times 2 squared plus 2 to the 6 over 6 plus c. And then I'm going to subtract f of 1. And when I plug in f of 1, I get 30 times 1 minus 10 times 1 squared plus 1 to the 6th over 6 plus c. Notice when I perform algebra, I get plus c minus c, and my c's cancel, which leaves me, if I do the mathematics here, with 10.5 square units of area. That is the exact value of this area, but Riemann sums can be used to approximate the area. If we go back to a simple example here of a graph, I can calculate the area of each rectangle, which is not perfect, but I can calculate by simply finding the width, the change in the x, delta x, times the value of that graph at that point. In this case, I'm using the midpoint C. And then I can add up all of these rectangles. In this case, there's 1, 2, 3, 4, 5 rectangles. So my n value is 5, and I will multiply delta x times f of whatever that c value is for those given rectangles, and then add them all up. And this is the summation sign that tells me that I'm adding. As an example, let's consider this graph. I'm going to divide this into 4 rectangles. Notice my delta x in each case is 1. So all 4 rectangles have an area of 1 times whatever the value of the function is at a place on the curve that I choose. For simplicity, I'm going to choose the midpoint of each of these rectangles. So I'll calculate f of 1.5, f of 2.5, f of 3.5, and f of 4.5. I'm going to use the function I was given, 1 over x, to calculate those values, which simplifies my function then to 1 times 1 over 1.5 plus 1 times 1 over 2.5 plus 1 over 1 over 3.5 plus 1 times 1 over 4.5. And when I calculate all of those values, I end up with an approximation of the area of 1.57. If I were to calculate the exact value, I would go from a, which is 1, to b of 5, the integral of f of x, which in this case is 1 over x dx. We know our integral there is the ln of the absolute value of x plus c. And based on the fundamental theorem of calculus, we're going to do f of 5 minus f of 1, which is going to give us the ln of 5 minus the ln of 1. And if we calculate the ln of 5, we're going to get a value of 1.6 minus the ln of 1, if you remember correctly, is going to give us a value of 0. So the actual value is 1.6, and our Riemann sum estimated it to be 1.57.